Okay, any question about the previous session? Today we want to finish our discussion about variational autoencoders, and then we will start a new model named blue models. Let's summarize what we have for variational autoencoders. Again, we see that if I can model the abstract representation or concept in an input x using a latent or unobserved variable z, then I can simplify the conditional distribution of what I observe. But the problem is that using this model, the likelihood of your data is the result of this integral, which is interactive. And this was the first problem, this is the first challenge. The solution to this challenge was to cast this integral as an expectation. Then we see that we can cast it as an expectation over the prior of latent. But again, we have another challenge that if we use a Monte Carlo estimation to estimate this expectation, we get high variance in our estimation. So we cannot train the model. Another solution, the solution for challenge 2 was to replace the prior using a sampling, another sampling distribution Q. But the problem that this solution create is that we should select Q now in addition to the model parameters. So we should select Q. What is the suitable Q? To select Q, we see that if we define a lower bound on the log likelihood or on the evidence, we can see that the best Q is the posterior that your model gives you the condition on what you observe. But again, the problem is that this best option is not tractable, so you cannot select Q to be equal to the posterior. This was challenge number 4. To solve this challenge, we see that our objective is to design Q such that we can minimize the distance between the KL distance between Q and your model posterior over latent given observed data. But the problem is that this posterior is not tractable. So we see that if we maximize elbow with respect to the parameters of the distribution Q, then it's equivalent to minimizing the KL divergence between Q and the model posterior. And so we see that how they are equivalent, because the summation of these two terms equal the evidence or the log of this likelihood, and the log of likelihood is independent of lambda. So maximizing one of these terms equal to, with respect to lambda, equal to minimizing another one with respect to lambda. And then the problem, so we should maximize L. We should maximize L with respect to lambda, and also we should maximize it with respect to model parameters. The next challenge was that calculating the gradient of the elbow with respect to theta and lambda. We see that calculating with respect to theta is straightforward, but calculating the gradient with respect to lambda is tricky because you have an expectation which is a function of a distribution, and that distribution is a function of lambda. So you cannot change their order similar to the gradient with respect to theta. The solution here was a trick that we called reparameterization trick, and you see that by changing by limiting the distribution Q to a Gaussian distribution family, then you can switch from the expectation over Q to expectation over standard normal distribution, and then you can change the order, and then you can use the Monte Carlo estimation to estimate this term. So this was the solution. So now you can maximize elbow with respect to theta and lambda because you have its gradient with respect to both of them. The next challenge was that you should maximize the elbow over data set. We see that we can replace the maximization of one sample with this term, which is the maximization over the whole data set. Was again the formulation generate another challenge, which was the interactability with respect to the number of training samples, because each training samples add another lambda vector to your optimization parameters. So the technique to solve this problem was amortization. The amortization is the technique that share a network, and that network is responsible to generate the optimum, the best accessible parameters for the sampling distribution. So instead of sampling over the parameters of this sampling distribution, you optimize it with respect to the parameters of this amortized network, and this network is responsible to generate the lambda for each input x. So independent of the number of the training data, you just have a network, and that network and the number of parameters for that network is fixed. So this will solve the interactability with respect to the number of training samples. But the last part that we talked about was to revisit the elbow objective function. We see that the elbow is defined as the expectation over the sampling distribution Q, which is parameterized by phi. Phi is now the parameters of that amortized network, and you do not see lambda anymore because lambda was dedicated to each sample. Now phi is shared among all samples. We see that elbow, the original definition of elbow was this definition, that the expectation over the samples coming from the sampling distribution of the log of the likelihood of the joint and the approximate posterior. We call it approximate posterior because the intent of this distribution is to approximate the intent of the Q is to approximate this distribution, which is the true model distribution over the latent given the data you observe. The objective of Q is to be this distribution, so we call it approximate posterior. Okay. But if you reformulate this term by adding and subtracting log of p theta of z, we reach to a very interesting reformulation. These two terms lead to the posterior over observed data given the latent, these two terms, and also these two terms result in a KL divergence between the approximate posterior and prior. We talked about the first term, again we review that, but the second term is also interesting that we talked today. Okay, the first term said that you should for an input x, you form the distribution by passing x through the approximate posterior distribution. This distribution generates two parameters, generate a mu and sigma 2. These two are used to form the distribution q phi of z given x. Then you sample from this distribution and calculate what you have here by Monte Carlo estimation, but you just have used one sample to estimate using Monte Carlo estimation. You can use more than one sample. For example, sample several z here and then average this function, but what is practically used is that you just sample one sample from this approximate posterior and then calculate the objective. And this is an estimate to the true expectation. Okay, let's see. This was the how you can let's say visualize the first term. The first term said that one input xi enter the network that generates the parameters for the distribution for the approximate posterior. At the output, you have your parameters corresponding to this xi for the approximate posterior, and then you sample from it and call it z. This is the z that is used to estimate the log of p theta of x given z. This is a sample from the posterior, and it is suitable and give you a lower variance. So you input z into the conditional model distribution over observed given the latent. Why? Because here we have the conditional. We do not have the joint anymore. We have a reformulated version, and we do not have the joint anymore. We have a conditional. So we input it into the conditional, and the conditional says that if you give me the z, I can give you a distribution over x. So you give the model a z, and then it generates the parameter for the distribution over x. And these are the parameters, and then you have the distribution. This distribution should be such that your input has the highest probability here. In this manner, you have trained a model. It means that the model is trained because the resulting conditional give the highest probability to your input data. Okay, this is the procedure we talk about, and just assume that we, for the case of the conditional over the observed given the latent is a normal distribution or Gaussian distribution, then the log of p theta of x given z take this form, and this form is very intuitive because you update your parameters such that the mean of the posterior here, the mean of the posterior here, this mean is as near to your data distribution as possible. And this is the best situation where they coincide. This mean coincide the observed data, because in this case your conditional distribution given the highest probability to xi. So this form is very intuitive how they be trained. And remember that when we talk about how phi parameters are affecting this term, we know that both mu and sigma 2 are result of z, which is the sample from a distribution parameterized by phi. So this term is a function of phi. Is it clear how phi affects this term? If it is not clear, look at this figure. I start with xi, input it into an amortized network. The network generates a mean and a variance. Then I generate z using the technique of reparameterization. It means that I sample from normal distribution and then multiply it by not the variance with a standard deviation. The square root of this value here was a problem. The previous session we talked about. The square root of this value is multiplied by your sampled data, and then you add the mean to the result, and then you have z. Then this z, which is a result of this network, enter the decoder, and then you generate mu theta and sigma 2 theta. So these two parameters are a function of phi. It is clear here because if you follow the graph, if you start back propagating, you come here, and then z again come here. From z you can back propagate here, and then back propagate to the model parameters, these amortized model parameters, which is phi. So mu and sigma 2 are function of both theta, as it is obvious because it is a subscript, and also phi. So this term should be optimized with respect to both theta and phi. Optimization with respect to theta is straightforward because you do not need any reparameterization trick. But optimization with respect to phi is a bit tricky because you need this reparameterization trick, and we talk about how you can apply reparameterization. Any question? Okay. What the next term? The second term, how it affect our model? If you pay attention here, what does this KL divergence mean here? What does it mean? The amortized network you are training must be near to the prior. What happened here? It means that irrespective of the input X, different observed data lead to different approximate posterior over latent given that data. We know that. But the second term here, try these distributions not to be very far from your prior distribution. I assume that this is your prior distribution over the latent. This term, the second term, tries different approximate posterior. What I mean different for different data samples. Q phi of z given, for example, x1 is here. The Q phi of z given x2 is, for example, here. Here you have different distributions in this space, and the number of these black circles is equal to the number of your training data. The second term tries to minimize the distance of the prior with respect to all of these distributions. How does it affect the model? This property result in a very interesting feature. Assume instead of sampling from the approximate posterior, the connection, you know that we start with X and then generate the approximate posterior over Z given X, then sample from it, then use this sample to generate data using model conditional. Okay? Now, assume this connection is cut. You have no connection to the X in the inputs. What type of Z can I generate so that the data here, the distribution here, if I sample from the distribution here, I result in meaningful data? You know, previously we see that if you input xi and then calculate this posterior over the latent given that xi, and then sample from that, a good model should give high probability to this xi, so it is meaningful. Because if you sample from this distribution, it give you generally it give you the highest probable x, and that highest probable x is near to your xi because the model is trained. Now, what happened if I do not have this connection and I want to generate some z so that the result of this decoding, just I want to use the decoding part, is a meaningful sample? Assume instead of sampling from any posterior, I sample from this, from the prior. What happened? I am sampling from something which is dependent on which is not dependent on x. No x affect this distribution. This distribution is independent of x. But I know that training the elbow or maximizing the elbow means minimizing this KL. It means that if you are sampling from the approximate posterior, you can also sample from the prior, and hopefully you see some meaningful data here. Why? Because this prior is near, all the posterior you trained are almost near to this prior in the KL sense. Does it make sense? I think it does not. You know, when you train the model, you try not the posterior to be very far from this prior, as I plotted here. All of the black circles try to be near to this green green sign. Okay, so they are near each other. Sampling from each of these blue circles may be equivalent or to some extent near to sampling from this prior. This just applies some modifications based on your inputs, just simple modifications. But generally they are around the prior. So if you sample from the prior, hopefully you are sampling from some of, from one of, for example, these black circles. And then you see the meaningful observed data corresponding to that black circles here. The second term provide you some, let's say, generation techniques. If we were not able to, sample, for example, Z, then how we can generate data? Because in generation we do not have access to an X. We do not have any X. We want this model. We have trained this model. For example, p theta of, we have p theta of Z. We have p theta of X given Z. We just, a trained model is meaning these two distributions. So you have a trained model and you want to generate samples. How you can generate? These properties show that you can generate samples with a trained model. How? You sample first from the prior, this prior, put it here, and then use the posterior over the observed given the prior and observe something. Because of this term in the objective function, you will observe meaningful data here. Because you are sampling from something which is not very far from the posterior distributions given different observed data. This is the property that the second term provides for you. Think of it, and if you have any problem, we can talk further. But pay attention that it means that irrespective of the data, I want the posterior to be around the prior. Because you are maximizing the elbow, which is minimizing this KL. And minimizing the KL means that these two distributions should be near each other, irrespective of xi. It does not mean that they collapse in the one point, but it means that they are near each other. Okay? So I can sample from the, for example, assume that I have a model trained over a nest. I can sample from the prior and call it Z, and then pass it through the decoder, is a mistake. Pass it through the decoder and generate the mean and the covariance, the variance value, and then generate the sample, the posterior distribution over X given Z. And then if I sample from this distribution, hopefully I see a valid MNIST image. Why? Because this prior is near to the approximate posterior for different MNIST images. We cannot guarantee that the resulting image is 3, but we can, to some extent, hopefully we see some meaningful data here, and you will see in your homework. Any question? Yes.
So Z is like a high representations of like digit 0 to 9, right?
Yes, exactly.
So when you sample from the prior, then the Z can be the representations of 1, then the generated image should be 1, right?
No, you know, if you train it over the complete MNIST data set, it means that you have no information that how you can generate the prior so that you get 1 here.
But it's random, right?
Yes.
Z is like a random representation of one of the digits.
Yeah, exactly.
Okay.
Random high-level representation, exactly, yes. Any question? But why we apply this very, to some extent, hard modeling for generating the data? One of the very interesting properties of variational autoencoders is the attribute vectors in code space. What does it mean? Assume I have 4 images. It's an image of smiling woman, an image of neutral woman, an image of smiling man, and an image of neutral man. Okay? So if I pass each of these images into a trained variational, we know how to train a VAE over these images. If I pass each of these samples from a VAE, assume that this Z of SW means that it is the latent of that smiling woman. Okay, I have a smiling woman, I have the approximate posterior function model. If I input this XSW into that model, I have a distribution over Z, and I can sample from that Z. Assume that this is just a visualization. We generally do not have the latent space dimension equal to 2, but just for the simplicity, assume that it is in the dimension 2. Then this Z, this is the resulting Z. It's a vector, and I plot that vector here. Also assume that I encode the neutral woman here using, again, the approximate posterior network. So I have 2 vectors here. Then if I subtract, assume that this smiling and neutral woman are the same exactly. All other features are the same, and the change is just the smile. In one of them, the image is a neutral, and in another, it is smiling. So if everything we talk about works, it means that in the latent space, just the difference is just related to smiling. It means that if I subtract these 2 vectors, I reach a vector of a smiling, the attribute vector of a smiling. It means that if I add the smiling vector to any neutral image, then I have a smiling version of that image, hopefully, if the VAE is working. So I just move the smiling vector into the origin, okay? So we have a Z of smile, a Z that hopefully, if the Z is added to the latent of a neutral image, it generates the latent of a smiling image, corresponding, right? Because everything should be the same, just the smiling, from neutral to the smile. So assume that then I encode the image of neutral man, and then add the smiling vector to the Z vector of smiling, to the Z vector of neutral man. What do I get? Yeah, hopefully I have a Z of a smiling man. That man is smiling. It means that the same man is smiling. And this is exactly the case that happened in VAE. It means that high-level information is exactly encoded into vectors. This is an example in this source. You can check this source. It has several interesting samples. But what are the attributes coded? You know, I have this original image. And using other images, I found the vector of smile and mouth open. I found 2 vectors with other images, okay, in the latent space, and then I have this image. So I encode the image of this image. In the latent space, I start adding a fraction of smile attribute to the Z and then decode it. Does it make sense how the procedure is? Yes?
Wait, so the length of that feature vector corresponds to the level of smiling, right? And the direction corresponding to like different features.
Right. The length, the direction is corresponding to the attribute, but you can play with the the length of the vector to make the attribute more or less, you know?
I see.
Yeah. If you add the direction is generally coded.
What about at the center?
What?
What the feature that is at the center? So let's say 0 zeros. What should I expect?
You mean centralize the feature?
Can you go back to the last?
Yeah, sure.
So let's say the vector is at the center, right?
Let's say the vector is at the center.
Yeah. So what would be?
No, you know, here just the direction is important.
Okay.
Yeah. So I know using this similar procedure, I previously found the smile and mouth open directions in the latent space of this trained model. Then I encode this image using the approximate posterior. Approximate posterior, how? I have this image, I use q phi of z given x. The x is this image, and I have a distribution over z. I sample from that distribution, I have z of this image. So I start to add these two vectors, smile vector and mouth open vectors. So you see that by adding the smile vector into the image and then decoding the resulting z. For each of these images, what happened? Assume that, I think we have something here. Oh, okay. Assume that this is the z vector of that image. This is the z vector of that image. How? By this procedure. And now I know the smile attribute. Assume that this is a smile attribute. I start adding this smile attribute with different length to the vector. For example, this length, this is the resulting new z. Then I input this z into the decoder. What is the decoder? The decoder is p of x given z new. And then sample from it. And then plot, show this sample. This is the sample x. I can see that by adding the smile attribute to my image, I have a version of this, the original image, where the smile is increasing. And also, in the vertical direction, I am adding another z vector to the latent, and that's the mouth open. And you can see that this is, if you assume that this is your reference image, your mouth, the mouth open level is increasing in the vertical direction. And they are all the result of manipulating the latent space. Yes?
How many smile vectors do we already know? There's only one direction, right? So why is there varying smile vectors?
You know, in that space, the concept in the concept that we consider is not encoded in its direction. You should find that direction, you know. For example, for this image, there are lots of concepts in image. For example, having glasses or not, having mustache or not. These are all concepts, okay? You should find those concepts vector. How? By having some images of similar abstract level, just difference in your concept. Then you find the difference. And with one pair of images, it is not possible. You must have several pairs, and then average over z for each of the pair, and that can be a great attribute vector for that concept. You can find lots of concepts here, and generally they encode different visual concepts in the latent space. Yeah. Any question? So I think we can, yes.
So how do you get the z for that specific original image?
Original?
Yeah.
Yeah.
We have a distribution of z, right?
Exactly.
So how do you know, do you just take the highest probability or of that distribution for the z representation of that original image?
Yeah. Assume I have, this is the distribution, and as you mentioned, this is a distribution, not a sample.
Yeah.
But the distribution is very simple. It is normal distribution as you remember, with mu of phi of x and sigma 2 phi of x times I. This is a normal distribution. You can easily sample from a normal distribution. You sample from that and assume that the latent space corresponding to your x is that sample. You do not work with the total with the distribution. You just work with this sample. Yes. You have a vector corresponding to this image in the latent space.
Also, will this be an or this one? All this would be an
Each of them have its own latent, you know. For example, this z for this image is just added, smile attribute is to some extent added, and mouth open is to some extent added, but because the amplitude and the ratio was a little, then you do not have any smile and any mouth open here, but by adding the coefficient of these two attributes, you can see that at the end, you have a smiling woman with open mouth.
No, I'm asking, will the probability of that image be quite low, very low, right? It will be out of distribution.
This is no, this is not out of distribution, but you, by encoding the concepts, find the latent of that image. Because this image is not in your training set. The model does not observe this image. It generates by the power of the model. Because the model can encode the concept in the latent, it can generate this image given this image, you know? But it is not, we cannot say that this is a low probability image because it's an image which is visually acceptable. So in the model, if you have it, it's a high probability. I mean that if you give it to the VAE, it gives you a high lower bound, high elbow. Why? Because it's a meaningful and acceptable image for a vision, for a face. Any question? Okay, that's the end of Variational Autoencoders, and I hope you can completely track the concept and understand the concept in the VAE. If you have any question about the VAE, we can talk about, but if not, we can start our discussion about a new model which is called normalizing flow. Any question about VAE? The total concept from the start. Can you follow the concept completely? What are the challenges? What are the solutions? Okay. So, we want to talk about another modeling procedure, which is again based on latent representation, but it is in a different way, completely different from VAE. So this is the table of contents, and we start each of them. We start by a very simple example, okay? Assume you have access to a base distribution which is P of Z. This base distribution is not suitable and does not fit your data distribution. This is your data distribution. How I generate these two images? This is sampling from a two-dimensional uniform distribution where each dimension is independent of the other one. You can see that. If I stay in one vertical line, I can observe a uniform distribution, and instead of staying in a horizontal line, again, I have a uniform distribution. So this is a two-dimensional uniform distribution, okay? But what my data is coming from is this distribution. It means that it has some rotation, it has some shrink, let's say expansion, but it is not, but I do not have access to something that can model the data distribution. This is a very simple example. We know that this is not also a practical distribution, and it cannot work in practice for a high-dimensional image, for example. But assume that for the simple case, I have this base distribution, but my objective is this more complex distribution. I call it P of Z, and it is P data of X. So I want to generate some, I want to transfer from this distribution to the this distribution. I want to know how to do this transformation. Okay. What is the general idea in the normalizing flow models? The general idea is to achieve the target distribution using these steps. First, I want to design a parametric transformation f of theta, and then calculate p theta of x. What does it mean? This is the original base distribution. I know that by applying some transformation over this distribution, I have a new random variable x. This is the base over z. And by change of variable formula, I know that if I transfer this random variable into a new random variable using this function, it means that the new random variable has a new distribution. It can be anything based on the function you are selecting. Assume that the result is this one, while our objective is this distribution, for example, okay? So because the transformation is parametric, I can change that parameter such that the resulting distribution is as near as to your data distribution. This is the objective. Can you understand what is the main concept here? I want to design this transformation such that the resulting random vector is coming from the data distribution, or it is near to this distribution. This is the base concept. Okay? What are the steps? The steps: first, we design a parametric transformation. So the transformation is parametric. It means that by changing the parameters, it has a new distribution. The parameters are your choices. You choose them, and we know that how to choose them, and we see in the next slides. Then calculate the resulting p theta of x. So if I transform the base distribution using this transformation, I have a new distribution. I call it p theta of x. Why p theta? Because this distribution is the function of theta. Because the transformation is a function of theta. So the new distribution is a function of theta over a new random variable x. So how can I design this theta? The new distribution should be such that give high probability to my data set. It is equivalent to maximum likelihood, or equivalently it is equivalent to minimum KL distance between P data and P theta. This is our objective. We want to minimize the distance between what we have and what we should have. And we know that minimizing this KL over the parameter is equivalent to maximizing the expected likelihood of your model data over the data coming from the data distribution. They are equivalent. So I have a tool to understand how suitable is this distribution. That tool is the likelihood of your data set. So I change the parameters such that the likelihood of the data set is maximized. So that's the best transformation. I think you catch the main concept here. I have a base, I have a type, I have a base, I have a transformation. That transformation is parametric. If I transform the base using that transformation, I have a new distribution. The new distribution is parametric. Why? Because it uses the transformation. I know that what should be the best one here. The best one is the one that gives high probability data coming from the data set using the KL distance. So I change the theta so that my data set has the highest probability. This is the total procedure or concept. Now we talk about everything. We talk about how to calculate p theta of x, everything. Is it clear what is the concept? Okay. So, change of variable, we know that, assume that z is coming from pz and x is f of z. Given that transformation is invertible, we can calculate the probability distribution p of x. We have the first limitation here, invertible. F of z must be invertible. Why? Because we want to calculate the density. If it is not invertible, in very special cases you can again calculate the density. But for the case of very complex distribution, this if the f is not invertible, calculating p theta of x is not possible. But if it is invertible, irrespective of the dimension and the complexity, you can easily calculate the p theta of x. We see that, how we can calculate. Do not worry about it. Okay, so f is invertible. This is the important point.
Question.
Yes.
About the invertibility of f theta of z. Is it so? What p theta of x is the resulting distribution. So why would we need it to be invertible? Because if we invert it, we're going back to like p of z from the diagram.
Yeah, and the most important point is that if it is invertible, you can easily calculate the p theta of x. If it is not invertible, for example, maybe you have in your statistics, probability and statistics course, you see that you can also, if, for example, this is x, this is y, if you have the distribution over x, also this distribution is not invertible, but you can calculate the distribution over y. But this is a very simple example. If it is a complex transformation and it is not invertible, calculating the p theta of x is impossible and interactive. We need it to calculate the distribution over x, the invertibility. Yeah. Any question? The most important point here is the change of variable theorem. How I can calculate p theta of x. What is the formulation here? And we want to talk about it now. If you do not remember from the previous courses, do not worry. I think we have all you need in this presentation. Okay. Assume that the base random variable, it means that it is a uniform over this box. I have a uniform distribution over this box. This is my base distribution. Okay? I have a transformation. I have a transformation f of z equal x, and the transformation is this way. X, the first dimension is 2z1 minus z2, and the second x2 is 2z1 plus z2. If you calculate the point, the transformations of each point, because of the type of this transformation, which is an affine transformation, the parallel line will be preserved, so you have another distribution like this here. So by changing from z coordinates into x coordinates, my distributions from this shape transforming to this new shape. Okay, I know that the PDF for the base distribution is 1/4 in each point. Why? Because the area of this box is 4. 2 times 2 is 4. So the PDF P of z equals 1/4 for z1 and z2 between 0 and 2. this is the PDF of original or the base distribution. This is the PDF over the base. Okay. The trivial inference about the distribution over the x in the x distribution is that each point in the z space is equivalent to another point in x space. We can calculate. If you give me the z, I can give you the x, and vice versa, because the transformation is invertible. So you have a point-to-point correspondence between these two spaces. So I can conclude that if pz here is equal to 0.25, again px here is also equal to 0.25. Because we have point-to-point correspondence. Every point here have a corresponding point there, so each of them have the same probability. So also assume that I have an event. Event means a subspace of the sample space. What is this? What is the subspace here? The subspace is this red area here. This red area, the corresponding area here is this red area in the x space, and if I calculate, these are equivalent events. Why? Because I use the transformation to transform s to s prime. So they are equivalent, and I expect that they have equal probability. So let's calculate the probability for each of these two areas. Okay, for the first one, I know that because the distribution here is uniform, I can calculate the area of this red region, and the area is equivalent. Area times the probability is equivalent to the probability of the event. The PDF times the PDF equivalent to the probability of event. So the probability of event equals the area of S times the P of Z. The area, if you calculate, is 1 over 2 or half times 1 over 4, which is the PDF, equal 1 over 8. This is the probability of this event in the original base distribution. So let's transform in the X space. In the X space, if you can, again, we know that because here we have uniform distribution, we have uniform here, the probability of S prime is equal to the area of S prime, and if I calculate the area of S prime, I'll get 1 over 2. And this is a contradiction. It seems that we have a contradiction. Why? Because these two events are equivalent. It means that I transform each point of the original space into the X space. So I expect that the probability of the S and the probability of S prime is equal. But the result is completely different. What is the problem? What is the problem? Let's think of the complete space. We know that the complete space, the probability of the sample space equal to 1. So if I calculate the probability of the sample space in the Z, I can get the summation equal to 1, which is expected. So it seems that everything works here. But if I calculate the probability of sample space in this X space, I get 4. It is contradiction with axioms of the probability axioms. The probability of the sample space equal to 1 everything.
Too many root hamster to copy to fix.
Exactly. Yeah. We want to reach that point. Exactly. Yes. Yes. What is the point? It seems that here something here is not correct, and it is evident that the thing that is not working is 1 over 4. Although our intuition that there is a point-to-point correspondence between these two spaces seems logical, but the problem is that when you transform from this space into the new space, the area is changed. The area of your sample space is changed. So if you preserve the value of the PDF, you definitely reach to this contradiction. what is not working? What is our problem here? The problem is that by changing the random vector z using a transformation, we do not definitely get the same value of the PDF in the resulting space. And the change of variable theorem talk about how to modify the PDF so that the resulting so that you can find the distribution in your new space. What is the suitable P of X in your new space? We know that definitely 1/4 is not the correct PDF in the X space. So we want to talk about the change of variable. Change of variable is the technique that helps you to understand what is the distribution in your target space. So we know that the simple correspondence is not working. Why? Because you have change of density. You know, this transformation means that especially these two numbers, means that the density of point is going to be changed between these two spaces. And the change of variable theorem will easily talk about how you can update your PDF from the base space into the target space. So we want to talk about the change of variable theorem. Okay, assume that Z is in RD is a random vector with base distribution PZ of Z. Just for this model, I use PZ of Z in the starting. But we know that if I write down PZ, we know everything, that this is the distribution in the Z space. But because they are in the same dimension, for the clarification, I use PZ of Z. Okay, Z is passed through an invertible function f to generate a random variable x with a more complex distribution. We denote the inverse function by f minus 1, and which we call it g. So x is f of z, and z is g of x. F and g are g is the inverse function of f. Then this formulation, which is called the change of variable theorem, tell you how to update the PDF if you use the F transformation. The distribution in the target space is equal to this is what we applied before. Okay, this is what we applied before. We said that there is a point-to-point correspondence. So again, PZ is valid in the X space. So we put 1/4 for the X space too. But the change of variable said that there is a correction factor, or there is a normalization factor to update the distribution from the base space into the target space. And this is what we should multiply to have the correct distribution in the target space. So what happened? It means that you have a point x, and you want to know what is the probability of this x. First, you should find the corresponding z, and we know that z is g of x. G is the inverse. Okay. Second, I calculate pz in this point. Let's talk about one point: x star, g, z star. We calculate the distribution of z star, and also this is not the PDF, the PDF in the x star points. You should multiply the value by the determinant of the Jacobian of g in the point x. What does it mean? We know f, so we can formulate g. We can formulate g, so we can calculate its Jacobian. Its Jacobian is d by d matrix, and then this d by d matrix you should evaluate it at your point x star. We want to talk about one point. We calculate the Jacobian in one point and take the determinant. The determinant of the matrix can be calculated easily, and then take the absolute value and then multiply that absolute value with the PZ of z star. This is the valid PDF at point x star. Or equivalently, you can use the Jacobian of f. Because g and f are inverse functions, g is the inverse of f, this determinant is inverse of this determinant. So you can use them interchangeably. This is the point that we miss. This normalization is the point that we miss. So the general idea is to select a sample-based distribution P of Z, select a flexibility is very important, and invertibility is important for your the transformation f theta, and assuming the observed random vector x equal to f theta of z, we calculate the exact distribution over x using the change of variable. What happened here in comparison to VAE? What happened?
Latent, the spaces.
Yeah, here there is a point-to-point correspondence between latent and observed. It means that you do not need to, for example, to infer z. Previously, we have the approximate posterior, the q phi of z given x. But here, the distribution is exact. It means that if you have an x, you have a corresponding z. And you can also write down the formulation here. And also the change of variable theorem can exactly provide the functional form for the distribution over target. It can marginalize out to some extent z and give the exact distribution in the target space. So here you do not have anything with that integral and that challenges that we have in the VAE. But the limitation here is that the transformation is invertible. In VAE, any transformation can be considered. We do not exactly consider, but in VAE, we do not limit in this space. But here, we have this limitation. It means that z and x are of the same dimension. When x and z are of the same dimension, there is no bottleneck. The bottleneck in the VAE, for example, x is 1000 by 1000 image, but z in the VAE. But z is, for example, 100. It means that from 1 million, you go to the 100 and then again to 1 million. This bottleneck is provide the abstract representation in the latent space in VAE. And you can easily encode concept, meaningful concept in Z. But here you have again 1 million dimension latent Z. And there is no bottleneck. There is no bottleneck to force the model to learn some meaningful things in the latent space. So the latent space cannot be interpreted as VAE. You cannot find the direction of some concept in the latent space of flu models. Okay? This is we will talk about it, but just to have an idea of the difference, you can think of the topics we talk. So let's return to our simple example. We have a simple example where x was a function, was a transformation over z. And now we wanted to consider a parametric transformation. We have 4 parameters, theta 1, 2, 3, and 4. And using these 4 parameters, you have a transformation over z, which leads to your target space. Okay. Let's assume that PZ again is 1 over 4, which is uniform for a box. And f theta is this function. So the correction factor, the Jacobian here, is this very simple. The Jacobian, we have the definition of Jacobian. The Jacobian here is the determinant of this matrix. So instead of just considering 1 over 4 for the p theta of x, you should update it using the ABS value of the Jacobian, the determinant of the Jacobian. And you can see that this factor solved every problem we see in the starting slides. So here I just add this normalization value based on the change of variable theorem. So let's talk about our example. Our example we talked about before. Again, we have exactly the same transformation. This is exactly the same transformation we see before, and which lead to a contradiction. Here, then the distribution in the target space is divided by 4. And where does this 4 come from? From these theta 1, theta 2, theta 3, and theta 4. If you calculate them, you will reach to a number 4, and you should divide the 1 over 4 by 4, and which is the result 1 over 16. This is the valid distribution in your targets. And what solve the problem? The change of variable theorem. The change of variable theorem normalizes PZ of Gx, which is the denominator here, by normalizing factor. Clear? So we have so let's talk about the event. The event we see before. The event was this red region. In the original space, it has the probability of 1 over 8. Here again, you have the probability of 1 over 8 by the modified PDF in the target space. We previously used 1 over 4 here. Now we use 1 over 16 with this valid number. So everything is working now. Do you understand how we update the PDF? Clear? Yes.
So it's clear how the normalization comes in. What I don't understand is the intuition behind it, like why the partial derivatives first order would actually result to the normalization. Like why is the Jacobian special? I don't understand.
You know, the Jacobian is exactly understanding how the point y. You know, this example is very special because it is uniform. What happened if we are working with very complex base distribution? Assume that the base distribution is Gaussian. Every point will be changing. This is very special because in all the points here, the Jacobian is fixed. Also, the distribution is fixed. The Jacobian is 4. The distribution is 1 over 4. So everything is simple. But the point is that the Jacobian, assume that you have, if you have not, let's say, uniform, assume this is your area, but inside this area, everything is not uniform. It's very complex, okay? Assume I zoom in a differential box. This is x1, this is x2, this is x1 plus d, this is, let's say this is x1, this is x1 plus d of x1. Just a differential addition to x1. It means that inside this box, I can consider everything to be constant, both the probability and the transformation, okay? This is x2, and this is x2 plus d of x2. Jacobian understand how the area change. You have a F transformation, and you have, oh, sorry, everything is right. This is Z. This is Z, because we are in the base space. Z, we are in the base, Z. Everything is Z here. You go by F theta, you go to X. X2, X1. Jacobian understand how this image area is changed when you go from the base space into the target space. For example, this is changed to this new shape. It's based on the Jacobian and the positioning. Okay, let's talk about the similar. The Jacobian understand in this point you have P z of z1 and z2, this vector. Why we can consider it constant? Because we are in the differential space. You just add a difference, a very small value to z1 and a very small value to z2. For this space, you are at the one point of your transformation, which is f theta of z1 and z2. Just one point. And that point has a Jacobian. Jacobian of f in the point, again, z1 and z2. This matrix can understand how the area is changing when you are transferring from the base into the target. For example, here the area, and it's just a typical, the area is dz1 times dz2. It can understand what is the area here. It is not you should calculate it as a function of dz1 and dz2. And the Jacobian can understand what is the area here and update everything. So that in the complete space here, you have equal to 1. The summation is equal to 1, the integral. Yeah. The Jacobian is responsible for updating the area. Or, for example, the density change. Because these numbers change the density in the sample, and if everything is equal to 1, the multiplication is equal to 1, it means that you have z1 minus z2, z1 plus z2. Because there is no change in the density, you will see that the Jacobian is also equal to 1, and everything will be similar in the both spaces. Just the shape is maybe changed. So do not consider the change of variable theorem as simple as here. The change of variable theorem should be applied to each point in the input space or in the base space to generate the corresponding point in the target space. But here, because everything was fixed, it means that the Jacobian is fixed, the PDF is fixed, constant. Everything is constant, you can easily calculate everything here. But we see that in the case of normalizing flow, everything would be much more complex. So the next thing that we will talk about in the next session is how to use this transformation to update the parameters of your transformation such that the resulting distribution in the target space is as near as possible to your data distribution. Yes?
Can we assume this transformation is always linear?
What?
Is the transformation always linear?
No, not at all. Yeah, you will have lots of nonlinearity in transformation. Yes?
In such a scenario, if suppose there is a nonlinear transformation, so I draw samples in Z space from uniform, the distribution might change in the X space.
Yeah, exactly. In the X space, you do not have any uniform anymore. And this is our objective, because the data distribution is much complex than we believe. For example, uniform, Gaussian, these types of distribution. So the change of variable can increase the complexity so that the distribution in the target spaces can be calculated easily. We do not have the problem of VAE. VAE is lots of problem to marginalize out Z to have the P of X. We see that we...
But in such a scenario, how do you control the invertibility of this?
Oh yeah, that's a trick. That's the trick, because especially if you not only you should control the invertibility, but also you should think of this value. You should think of these values. They can be easily calculated, because you want to calculate them for several times during training.